This is Aaron Schwartz, one of the secondary math specialists with Montgomery County Public Schools. Today's video is how we're going to introduce the concept of quadratic functions, but we're actually going to do it by observing transformations in generic functions. And this is really important because quadratic functions can often hide some of the key learnings we want students to observe. In Unit 4, Topic 1, the students have learned to model quadratic relationships with expressions by exploring patterns and connecting to area. One of the key ideas as we go into Unit 4, Topic 2, is that for a function f of x, a times f of x, f of ax, f of x plus k, and f of x plus h, change the value of the function in specific and observable ways. Some helpful skills that students have learned. Algebraic expressions can be used as models of patterns. This is done in IM and Math 8, and it's started in Algebra 1 as well. Now, to do this, we're not really going to use much of the screencast. We're actually going to go to Desmos, because viewing this on a digital graphing calculator that is dynamically changeable makes the observation process so much easier for students and so much clearer. Now, just for the record, we could actually do this just as easily in GeoGebra, but Desmos has some usability features that make it very nice, especially for students who are viewing online graphers for the first time. So I'm going to go ahead and click my link. It's going to take me to Desmos, and I just want to start graphing. I have this enormous graph, and I'm going to change it just to make the viewing a little bit easier. For one thing, I want to put this in projector mode so that the numbers are nice and bold. And I'm going to get rid of these minor grid lines and just focus on these major grid lines. Now, normally we start with a quadratic, but that's not what we're going to do in this video. In fact, one of the best functions to use to better understand transformations are actually sine waves. So I'm going to create a function, a sine of bx minus h and plus k. Now you'll notice on Desmos that I get this question, add a slider, and it lists the variables and it has all. We want to add a slider for all of them. Now I'm going to go ahead and add another function, but the purpose of this is not actually to view yet. So I'm going to add a similar function, a times the quantity bx minus h and quantity squared plus k. It's a quadratic. And I'm going to go ahead and click on this graph right here because I want to hide it for now. Let's start playing around with those variables. Let's actually start with our bottom and work our way up. Let's start with k. If I were doing this in a classroom, I might give one Chromebook to every 2 students or one Chromebook to every 3 students. And I might assign roles, such as one student is supposed to manipulate the graph, while other students are supposed to either describe what's being changed about the graph, and one might be the recorder for the group, because we want to share out what we've done. There's also no reason for an activity like this to have one Chromebook for every student. So let's start moving around K and seeing what happens. Notice as we move k around on the slider, the graph appears to be moving up and down. This is exactly what we want students to notice. But what we want to refine with our students is when k is positive, what's happening? Is it moving up or down? When k is negative, is it moving up or down? And so we want to help students get specific rules. Now let's look at moving around h. Students may say that h seems to make the graph move forwards or backwards. And that's a very good observation. we want them to refine their language a little bit more to talk about moving towards the positive x direction or the negative x direction. If they're not quite precise on the rule with regards to the sign of h, that's okay at the moment. We really just want them to focus on the moving left and right. Now, one of the problems with a quadratic is that the a value is a vertical dilation. But a vertical dilation is extremely hard to see. In fact, if I change a on the quadratic, some students are going to perceive that the parabola is either getting wider or narrower. And based on viewing just a quadratic function, that's a reasonable conclusion, especially when we haven't explored a table of values. I'm going to reset this to 1. I'm going to turn off my quadratic function. I'm going to turn on my sine wave again. This time we're going to look at what a does. As I increase a, what do we observe happening? Students may say the waves are getting bigger or they're getting taller, and that's the key. They're actually changing their height. They are being scaled vertically. In fact, a is something we call a scalar, and it's scaling the graph in the vertical direction only. It's a vertical dilation. When we're viewing quadratics, that's really difficult for students to perceive, but this beautiful sine wave gives us that understanding very clearly. Let's go ahead and change that back to 1. Let's play around with b for a second. As I increase b, I see that I'm getting waves, or the waves are happening faster, or the number of waves per unit has increased, or the waves get closer together. There's a number of ways students may describe this. This has to do with what we call the frequency of the function. We're actually introducing the idea of b as increasing the frequency with which we see the waves over a given interval. So when we talk about b, that's actually changing the horizontal scalar, or the horizontal dilation of the graph. So when we talk about a and b, we want students to be precise, and we want them to recognize that a, in the case of sine, is only changing the amplitude. And so it's increasing only in the vertical direction, whereas b is changing things in the horizontal direction. Let's go ahead and change this back to 1. Let's turn off our sine wave. Let's turn on our quadratic. We now have a sound foundation for exploring the transformations of quadratics. One of the most difficult rules for many students to understand is this relationship with the minus h. There's actually a lot of very powerful features in Desmos. And if you know a little bit of LaTeX, you can really enhance your graphs and enhance the student experience. For example, I can drop in a point. And at this, I'm going to drop in this point at 2.5, 2.5. And I'm going to choose to label this point. And this point is not really about labeling that particular ordered pair. It's actually going to give me a place to drop an equation. So I'm going to use this back apostrophe that's underneath the tilde button. It's in the upper left-hand corner of a keyboard. And that's going to activate within Desmos the key to look for a LaTeX-like expression. What I'm going to do is type in y equals, this is going to be where we pull in our LaTeX skills, $, open curve bracket, a, close curve bracket. What that's telling Desmos to do is to read the variable a and just put it on the screen. Parentheses, x minus, actually I want a space in there, minus space, $ curve bracket h, close parentheses. I'm going to raise it to the second power, plus $ open bracket K. And this is telling Desmos, put in the values for A, H, and K in this expression that we're going to display on screen. And I'm going to close off with that back parentheses again. And now all of a sudden I have this beautiful equation on my graph. Just to make it a little bit larger, and I'm going to actually turn off the visualization of the point. And there we go. We have this beautiful equation. This is really key because now I'm going to change H to a negative value. I'm going to change H to -3. One of the most difficult things that students encounter when looking at quadratic transformations, and transformations in general, is that there's a perception that when H is negative, we're actually moving the quadratic to the right, and when H is positive, we're actually moving it to the left. For mathematical reasons that we're not going to explore in this video at this moment, what we really want students to notice is that it's not that it's left is positive and right is negative, it's that you're subtracting a negative or you're subtracting a positive. And that we take the shorthand of the double negative appearing as a positive. So what's happening is when we do minus a -3, we actually are going to the left. It's just that when we simplify minus a -3, we generally write +3. So I hope that this video helps teachers create classrooms where students explore math, observe patterns, and develop conceptual understanding. If you have questions, comments, or have a video idea, please email me at the address below.